Alright, let's go. Number 10. The Immortal Jellyfish of the Cosmos. In 1967, astronomer Halton Arp published his Atlas of Peculiar Galaxies, cataloging 338 objects that defied every rule of cosmic evolution. Among them were galaxies that should have burned through their fuel billions of years ago. Stars consume hydrogen at predictable rates. Galaxies age, redden, and die as their stellar populations exhaust themselves. The mathematics of stellar evolution are among the most tested equations in astrophysics. We know how long stars live, we know how galaxies should die, and yet scattered across the observable universe, astronomers keep finding galaxies that refuse to follow the rules. They call them green pea galaxies and blueberry galaxies, compact systems burning with the light of furious star formation despite being older than Earth itself. Some of these galaxies have been forming stars continuously for over 10 billion years, a feat that should be mathematically impossible given their limited gas reservoirs. By every calculation we can run, they should have exhausted their fuel eons ago and faded into red dwarf graveyards drifting silently through intergalactic space, but they haven't. They burn on, bright and young and impossible, as if something keeps feeding them material from a source we cannot detect. The standard model of cosmology has no explanation for their persistence. Some researchers propose dark matter halos, channeling cold gas into their cores. Others suggest intergalactic filaments delivering fuel through invisible cosmic rivers. None of these explanations have been confirmed. The mathematics of what we can observe simply doesn't add up. These galaxies are cosmic zombies, refusing to die on the schedule physics demands. The truly unsettling part isn't their existence. It's what they imply about our models. Every calculation we make about the age and fate of the universe assumes we understand how galaxies consume fuel and die. If even a fraction of galaxies can cheat this process through mechanisms we don't understand, then our entire timeline of cosmic evolution might be wrong by billions of years. The universe you think you live in, with its predictable birth and inevitable heat death, might be running on rules we haven't yet learned to read. Number 9. The impossible hexagon of Saturn. In 1981, NASA's Voyager, one spacecraft captured images of Saturn's North Pole that scientists initially dismissed as a rendering error. At the top of the gas giant, perfectly inscribed into the swirling cloud bands, was a hexagon, not an approximation, not a rough six-sided pattern, a geometrically precise hexagon roughly 30,000 kilometers across, large enough to contain 4 Earths side by side. Storms in planetary atmospheres don't form hexagons. They form spirals, cells, vortices, chaotic turbulent shapes driven by Coriolis forces and convection. The laws of fluid dynamics predict curves, not corners. When Cassini confirmed the hexagon's existence in 2006 and watched it persist for years, atmospheric physicists faced a structure that seemed to violate basic principles of how gases behave at planetary scales. The hexagon has now been observed rotating in lockstep with Saturn's interior for decades. It has changed color, shifting from blue to gold as seasons progressed, but its shape has never broken. Its edges remain sharp enough that you could draw them with a ruler. Each side moves at approximately 100 meters per second, and the entire structure completes a rotation every 10 hours and 39 minutes, synchronized with Saturn's magnetic field in ways we cannot fully explain. Laboratory experiments have managed to produce hexagonal patterns in rotating fluids under very specific conditions, but nothing approaches the scale or stability of what exists on Saturn. The planet's hexagon has persisted through solar cycles, seasonal changes, and immense energy inputs that should have disrupted any delicate standing wave pattern long ago. We can model it approximately. We cannot explain why it refuses to break. What haunts atmospheric scientists is the question of how long it has been there. The hexagon could be decades old. It could be millions of years old. There is no mechanism in our current understanding of planetary atmospheres that should allow such a structure to exist, let alone persist. It sits at the top of Saturn like a signature carved into the clouds, a reminder that the universe is building things we have no equations for. Number 8. The cold spot in the cosmic microwave background. In 2004, astronomer Patrizio Vielva and his team at the University of Cantabria announced the discovery of something that should not exist in the early universe. Hidden in the cosmic microwave background, the afterglow of the Big Bang itself, was a region of space roughly 1.8 billion light-years across where the temperature dropped significantly below the cosmic average. They called it the CMB cold spot, and it has haunted cosmology ever since. The cosmic microwave background is supposed to be uniform to within tiny fractions of a degree. It represents the universe at 380,000 years old, when matter first became transparent to light. The standard model of cosmology predicts small fluctuations, the seeds of galaxies in structure, but nothing approaching the scale of the cold spot. Statistically, a feature this large should appear in our universe with a probability of roughly 1 in 50. Not impossible, but deeply unsettling. Initial explanations assumed it was a massive supervoid in the foreground, a region of space containing fewer galaxies than average, cooling the light passing through it by gravitational effects. But in 2015, a survey of the area found no supervoid large enough to explain the temperature drop. The cold spot is real, and nothing we can see accounts for it. Some physicists have proposed something far stranger. The cold spot might be evidence of another universe. In theories of eternal inflation, our universe is one bubble among countless others, expanding in a vast multiverse. If another bubble universe collided with ours during the earliest moments of existence, the impact could have left a bruise in the cosmic microwave background, a region permanently scarred by contact with a reality outside our own. This hypothesis has not been confirmed. It has also not been ruled out. The cold spot remains one of the only features in the observable universe that mainstream physicists have seriously proposed as possible evidence of other universes touching our own. Every time you look at a map of the cosmic microwave background, you can see it, a dark wound in the fabric of creation, placed there by something we cannot identify and possibly cannot access. The universe has a scar, and we do not know what caused it. Number 7. Methuselah, the star older than the universe. In 2000, astronomers using the Hubble Space Telescope measured the age of a nearby star designated HD 140283, located just 190 light-years from Earth in the constellation Libra. The results were impossible. The star appeared to be 16 billion years old. The universe itself is 13.8 billion years old. Nothing in the universe can be older than the universe. Yet the measurement kept coming back the same. Astronomers nicknamed the star Methuselah, after the biblical figure who lived 969 years and began a decade-long effort to figure out what had gone wrong with their calculations. The problem wasn't instrumental error. Hubble's measurements were among the most precise ever taken for a nearby star. The problem was that Methuselah's chemical composition, brightness, temperature, and distance all pointed to an age that violated the foundational timeline of cosmology. In 2013, astronomer Howard Bond and his team refined the measurements using improved parallax data and stellar evolution models. The revised age came in at 14.46 billion years, with an uncertainty of plus or minus 800 million years. Within the margin of error, the star could be as young as 13.66 billion years, just barely younger than the universe. The problem eased, but it didn't vanish. Methuselah still sits at the absolute edge of what physics allows, so close to the age of the universe that any small error in our cosmological constants would push it back into impossibility. And Methuselah is not alone. Other extremely old stars have been found throughout the Milky Way's halo, metal-poor ancient suns that formed when the universe was barely a few hundred million years old. Their existence requires that the first generation of stars formed and died with extraordinary speed, seeding the cosmos with heavier elements fast enough to create Methuselah and its siblings within a window of time that should be too short for such complex chemistry. What makes this unsettling is the implication. Either our age for the universe is wrong, or our models of stellar evolution are wrong, or something allowed these stars to form through processes we don't yet understand. Methuselah is not a mystery that has been solved. It is a mystery that has been softened. The star is still there, 190 light-years from Earth, burning at the edge of what physics permits, older than it has any right to be. Number 6. The Tabletop Time Reversal. In 2019, a team of physicists led by Gordy Lesovic at the Moscow Institute of Physics and Technology did something that should be impossible. They reversed time. Using a quantum computer, they took a system of qubits and engineered their evolution backward, forcing particles to return to a previous state in apparent violation of the second law of thermodynamics. The second law is arguably the most unbreakable rule in all of physics. It states that entropy, the measure of disorder in a system, always increases over time. This is why cups shatter but never unshatter, why heat flows from hot to cold and never the reverse, why eggs cannot unscramble themselves. The arrow of time points in one direction, and physics has no mechanism for turning it around. And yet, in a carefully controlled quantum environment, entropy moved backward. The Russian team demonstrated that for 2 qubits, time reversal succeeded 85% of the time. With 3 qubits, the success rate dropped to 50%. The experiment didn't violate the second law in any global sense. The entropy of the larger system still increased, but within the isolated quantum region, the arrow of time ran backward in a way that classical physics says should never happen. What makes this truly disturbing is what it suggests about reality at its smallest scales. If the arrow of time can be reversed, even locally, even briefly, then time itself is not the fundamental thing we believed it to be. It becomes an emergent property, a statistical illusion created by the behavior of vast numbers of particles, rather than a fixed dimension woven into the fabric of existence. The experiment cannot be scaled up. Reversing time for a cup of coffee would require calculations beyond what any computer in the universe could perform. But the principle has been demonstrated. Somewhere in a Moscow laboratory, for a fraction of a second, the universe ran backward. The implications reach into places we are not prepared to follow. If time can flow in reverse under the right conditions, then our understanding of causality, of memory, of the permanence of the past might all be artifacts of scale rather than fundamental truths. The universe may not remember events the way we assume it does. Number 5. Dark flow and the edge of everything. In 2008, astronomer Sasha Kashlinsky and his team at NASA's Goddard Space Flight Center published results from a study of galaxy clusters that produced a finding so strange many cosmologists refused to believe it. Hundreds of galaxy clusters across 1 billion light-years of space were moving together in the same direction at extraordinary speeds, pulled toward a point outside the observable universe. They called it dark flow. The standard model of cosmology predicts that on the largest scales, the universe should appear uniform. Matter should be distributed evenly, and galaxy clusters should move according to the gravitational influence of visible matter and dark matter within the cosmos. There should be no preferred direction, no cosmic current carrying entire regions of space toward anything. The universe should be isotropic, the same in every direction. Dark flow violates this principle completely. The galaxy clusters Kashlinsky observed are being pulled at speeds of up to 1,000 kilometers per second toward a region beyond our cosmic horizon, a place we cannot see and cannot reach. Whatever is pulling them exists outside the observable universe, beyond the 46 billion light-years of space we can detect with even our most powerful instruments. It is, by definition, unknowable. Some physicists propose that dark flow is evidence of structure in the universe that existed before inflation, the rapid expansion that occurred during the first fraction of a second after the Big Bang. Others suggested it might be the gravitational pull of another universe pressing against our own from outside. A few dismissed it as statistical error. The debate has not been resolved. Follow-up studies have produced conflicting results, some confirming dark flow, others finding it weaker or non-existent. The most recent analyses using data from the Planck satellite suggest the effect may be smaller than initially reported, but not zero. Something is pulling galaxy clusters toward a point we cannot observe, and we have no accepted explanation for what it might be. The thought is genuinely terrifying when you sit with it. There is a direction in the universe. Matter knows which way is out. Whatever exists beyond our cosmic horizon is massive enough to move entire galaxy clusters across billions of light-years of space, and we will never see it, never measure it, never know what it is. We are being pulled toward something, and the universe has drawn a curtain across the destination. Number 4, the superluminal neutrinos that weren't. In September 2011, physicists at the Opera experiment in Italy announced that they had measured neutrinos traveling faster than the speed of light. The particles had been fired from CERN in Switzerland to the Gran Sasso laboratory 730 kilometers away, and they arrived 60 nanoseconds earlier than light would have taken to cover the same distance. If confirmed, the result would have overturned Einstein's theory of special relativity and rewritten the foundations of modern physics. For 6 months, the physics community convulsed. Einstein's relativity is one of the most thoroughly tested theories in the history of science. Nothing with mass can exceed the speed of light. The equations are unambiguous, the experimental confirmations are overwhelming, and the theory underlies everything from GPS satellites to nuclear power plants. A faster-than-light particle would not just be a new discovery, it would be a catastrophe for physics. In early 2012, the Opera team identified the source of the anomaly. A loose fiber optic cable had introduced a timing error into their measurements. The neutrinos had not exceeded the speed of light. Relativity was safe. The physics community exhaled, and the story faded from headlines. But here is what the textbooks don't tell you. The error correction didn't fully resolve the mystery. Even after the cable problem was identified, certain aspects of the original data remained unexplained. More importantly, the entire episode revealed how fragile our confidence in fundamental physics actually is. For half a year, serious scientists at major research institutions could not definitively say whether the speed of light was truly a cosmic speed limit. The laws we treat as absolute are upheld by instruments and interpretations that can fail in ways we do not always notice. And neutrinos themselves remain genuinely strange. They oscillate between 3 different flavors as they travel, changing identity mid-flight in ways that required rewriting the standard model of particle physics. They pass through matter almost without interaction, with billions of them streaming through your body every second. They have mass, but we don't know how much. They might be their own antiparticles, a property that would violate several conservation laws we thought were inviolable. The superluminal neutrino result was wrong. But the universe still contains particles that bend our rules at the edges, and every time we look at them more closely, something new refuses to fit. Number 3. The quantum eraser and the retroactive past. In 1999, physicist Marlin Scully and his colleagues performed an experiment that suggested the present can change the past. It is called the delayed choice quantum eraser, and more than 2 decades later, physicists still argue about what it actually means. The experiment builds on the famous double-slit experiment, in which particles like photons or electrons behave as waves when not observed, and as particles when measured. The act of observation collapses their wave function and forces them into a definite state. This is strange enough on its own, but the quantum eraser takes it further. In the delayed choice version, the decision to observe or not observe the particle is made after the particle has already passed through the slits. Somehow, the particle's past behavior, whether it acted as a wave or a particle, depends on a measurement that hasn't happened yet. The experiment has been performed many times with increasingly sophisticated setups, and the results always agree. The future measurement determines the past behavior. Causality, as we experience it in everyday life, seems to break down at the quantum level. Physicists have offered various interpretations to soften the blow. Some argue that nothing is actually traveling backward in time, that we're simply selecting which version of reality we measure after the fact. Others invoke the many worlds interpretation, suggesting that all possible outcomes occur in parallel universes, and we only observe the one consistent with our measurement. None of these interpretations is universally accepted, and all of them require abandoning something fundamental about how we think reality works. What makes the quantum eraser genuinely unsettling is that it is not a thought experiment. It is a repeatable laboratory result. When you measure a particle in the present, something happens to its past. The past is not as fixed as our intuition insists. At the smallest scales, time behaves like a conversation between moments rather than a one-way street. The implications extend beyond the laboratory. If the past can be influenced by present measurements at the quantum level, then the entire history of the universe might be more fluid than we assume. Every moment in the 13.8 billion years since the Big Bang might still be shifting subtly, nudged by observations happening right now in places we cannot see. The universe you remember may not be the universe that actually happened. Number 2, the proton that shouldn't decay. The standard model of particle physics, our most successful theory of how matter works at the smallest scales, predicts that protons should be unstable. According to grand unified theories developed in the 1970s, protons should eventually decay into lighter particles, falling apart after an average lifespan of roughly 10 to the 34 years. That is a 1 followed by 34 zeros, a number so large that the universe itself has existed for only 10 to the 10th years, vastly shorter than a single proton's predicted lifetime. Still, with enough protons watched for long enough, we should see some of them decay. Physicists built enormous detectors to find this decay. The Super Kamiokande experiment in Japan, completed in 1996, consists of 50,000 tons of ultra-pure water held in a tank deep underground, surrounded by more than 11,000 light sensors. With that many protons in the water, statistics predict we should observe proton decay events regularly. We have been watching for decades. We have seen nothing. 0 confirmed proton decays, not 1. The proton is not just stable, it is stable to a degree that exceeds the predictions of multiple grand unified theories. Every version of physics that predicts proton decay has been constrained, narrowed, and in many cases ruled out by the silence inside Super Kamiokande. The theories that were supposed to unify the fundamental forces of nature keep failing because protons refuse to fall apart. This is a quiet catastrophe for physics. The grand unified theories were supposed to explain why the universe contains matter at all. They were supposed to reveal how the forces of nature emerged from a single unified force in the first moments after the Big Bang. Without proton decay, these theories lose their anchor. We are left without an explanation for why matter exists, why the universe is not just a sea of radiation, why you are here to read these words. The proton is too stable. It refuses to obey the theories that predicted its death, and every year that Super Kamiokande watches and sees nothing, the mystery deepens. Somewhere in the equations of physics, there is a mistake we have not yet found, and the proton is patiently waiting for us to discover it. Number 1. The universe itself. In 1998, 2 independent teams of astronomers measuring distant supernovae made a discovery that should not have been possible. The expansion of the universe was accelerating. A force they could not identify was pushing space apart at an increasing rate, overcoming gravity on the largest scales and driving galaxies apart faster every year. They called it dark energy, and we still have no idea what it is. Dark energy accounts for roughly 68% of the total energy content of the universe. Dark matter, another substance we cannot detect directly, accounts for another 27%. The ordinary matter that makes up stars, planets, and human beings, everything we can see and touch and measure, accounts for less than 5% of reality. The universe is overwhelmingly composed of things we do not understand. But the problem runs deeper than mere ignorance. When physicists try to calculate the expected value of dark energy using quantum field theory, the prediction comes out wrong by a factor of 10 to the 120. That is a 1 followed by 120 zeros. It is the single worst prediction in the history of physics, an error so vast that it has been called the cosmological constant problem, and no one has solved it. Theoretical value for dark energy is either impossibly large or mysteriously small, depending on which calculation you trust. Neither matches the observed value. According to our best theories, the universe should either have collapsed in on itself within the first fraction of a second after the Big Bang, or it should have expanded so violently that no galaxies, stars, or planets could have formed. Instead, dark energy exists at precisely the value needed to allow structure to develop, life to evolve, and conscious observers to eventually ask why the universe exists at all. This is not a minor discrepancy. It is the most fundamental failure in modern physics. We cannot explain why the universe exists in the form we observe. Every calculation we run says it should not be possible. Every observation we make confirms that it is. The universe you live in, with its galaxies and oceans and memories, sits at the edge of mathematical impossibility, balanced on a value so precise and so unexplained that some physicists have stopped trying to derive it and simply accepted it as a brute fact. According to physics, the universe should not exist. And yet here you are, reading these words, inside a cosmos that broke its own rules to let you be here. The deepest mystery is not any single object or phenomenon within the universe. It is the universe itself, and the fact that anything exists at all. If you want to see more videos like this, click the video on screen now and make sure to subscribe.